will be given by Matthias Irlbeck. Matthias Irlbeck is a PhD student in his final year in Groningen of Tobias Müller, and he'll talk about Poisson-Voronoi percolation. So he'll be here until the end of this month, in case you're interested to talk to him. Please, Matthias, go ahead.
Thanks a lot for the introduction and for the opportunity to give my talk here today. So everything that I will present here was done in joint work with Zakar Kuluchko and my supervisor Tobias Müller. I hope that I will explain most of my talk, but if there's like anything unclear, if you have any questions, just feel free to interrupt me and ask me. All right, so first we maybe define a model that will be like the main topic of the talk today. So we want to randomly color in Poisson-Voronoi percolation, we want to randomly color subsets of the Euclidean d-dimensional space. And we do this in 3 very simple steps. So in the first step, we have a Poisson point process with some constant intensity lambda. And you may be already familiar with that, but just to recap, there's just a random number of points such that the number of points in each area follows a Poisson distribution with intensity lambda times, or parameter lambda times the volume of this area. And the number of points in disjoint areas are independent from another. So this is the first step. And in the second step, we associate the Voronoi cell to each of those points. And the Voronoi cell is just all the area that is closer to this random point than all the other points of the Poisson point process. And in the third step, we now color each cell to be black independently from another with some fixed probability P. And P is the parameter of the model, and we fix this before doing all of this. So one of the nice things is that the model is quite easy to define and also to visualize. So this was the first step. We get some random points now in the plane. The second step was the Voronoi tessellation. So here you see this will form some cells, and this is all the area that is close to that point, then all the other points. And in the third step, we now color the cells independently from another to be black. So here P is 1/2, and you see that this will create this coloring of the plane here. So this may be like now a bit zoomed in. You can also zoom out a bit more, and then maybe looks like this. So here again, P is 1/2. It looks a bit like maybe like an old TV screen, and we want to study those connected components here. But as like on my title slide, I said that we want to do this in high dimensions. Now we go 1 dimension up, and this is how it could look like in 3 dimensions. So you see this blue structures are the Voronoi cells. The green dots are the Poisson points, and some of the resulting polytopes are colored to be black here. And this may be now a bit chaotic. So here you can see like one connected component. So you see all those polytopes, they're next to each other. And what is like a nice property of this model is that if I say like that 2 cells are next to each other or adjacent, I mean that they share a phase. And one property is that they are adjacent if and only if they share a d-1 dimensional phase, because it was made out of a Poisson point process. All right, so maybe you're already kind of familiar with like ordinary. Yeah.
Something simple, but when they share a phase, they always share the whole phase. So
yeah, that's true. Yeah. And yeah, like maybe you're a bit familiar with like ordinary.
Right. From the picture at least.
Yeah, it's true. Yeah. And like maybe you're already familiar with like ordinary percolation, and that's a bit different because now we colored like those polytopes in space, and like ordinary percolation is a bit different because there you fix like some graph, and then you color the vertices of the graph. And most of the time the graph is deterministic. Like the most like prominent, for example, is like the like ZD or here Z2, and then you have like the grid, and you color each point independently with some property P, and then you want to study the resulting random subgraph. And like, yes, like I said, most of the time it's like a deterministic graph. And here we did a bit different things, right? But there's like some relation to it. So what you can do is you can define a random graph out of this plot that I just showed you. So, and this is then called the Delaunay graph. So what you can do is, so here you see the same picture on both sides. This is what you saw before. And what we now do is we form a random graph where the vertices are the points of the Poisson point process. And we form an edge if the Voronoi cells are neighbors. So this is what you can see here now. And then we can do the same thing as before. We color the sides of this resulting random graph to be black with this probability P that we had as a parameter. You see it's like just the same picture on both sides. Here we kind of have the interpretation as like a random area that we color. Here we have a random graph, and we color the vertices of this random graph, and then it fits more into like the classical percolation scheme that you would normally have. And so there's one very important characterization of this adjacency, and this is the fact that 2 points, so here you have X and Y, they are adjacent, or they share the space if and only if there exists a ball that's now in blue here, with the 2 points on the boundary, but no other point inside this ball. So yeah, see it exactly here, and you can think about the ball having the center at one of the faces, and then yeah, the 2 points are on the boundary. This kind of follows from the definition of the Voronoi cell that something like this has to exist in order for the 2 points to share a face, and for the 2 sets to be adjacent to each other. So then when this exists, then I say that this Delaunay ball exists because like, the graph is called the Delaunay graph. But what's very important is that this ball is not unique, and there are like many different balls that I could have drawn here. I could have shifted it a bit to the right, and another ball would have existed there. But there exists a very simple related graph to this Delaunay graph. That's called the Gabriel graph. And in the Gabriel graph, we fix one very specific Delaunay ball. So we fix the ball where the center is in between the points, and the 2 points are again on the boundary of the ball. So here the Gabriel ball is drawn in red. And now in this Gabriel graph, I connect 2 points if this Gabriel ball has no other point of the Poisson process inside. So in this case, I would not connect X to Y because there's this point here blocking the connection. So every Gabriel ball is a Delaunay ball, but not the other way around. So it's a subgraph of another. And yeah, like with this ball, and of course mean the open ball, because otherwise this would be impossible, because then X and Y would be on the boundary, right? So yeah, this is like a related graph, and like a lot of results that I will show you, we will obtain for both the Poisson-Voronoi tessellation or the Delaunay graph, and also for the Gabriel graph, which is, like I said, a subgraph of it. And the nice thing about the Gabriel graph is that this ball now is fixed. There's like just a unique ball, and this makes it way easier to analyze than the other model. Right? Is there maybe already a question about like those two models? No? All right. So the main thing that we want to do in percolation theory is we want to say, when can there exist an infinite connected black component? So you can either think about having an infinite component of like polytopes that are colored that are next to each other, those clusters, or you can just think about the graph analog where you have an infinite, let's say, path of black points that are all next to each other in the Delaunay or Gabriel graph. And if this occurs, then we say that percolation exists. And what we can now do is we can define a threshold, like the critical probability, above which, so if P is above this critical probability, there can exist infinite component, and below that, there are no infinite components almost surely. And about those models, the nice thing is that here this critical probability is actually independent of the intensity lambda. So intensity lambda was the parameter of our Poisson point process, because we can just zoom in and zoom out, and this will not destroy any infinite component. So you can just like scale every point with some constant, then you will get a Poisson point process with another intensity, but the infinite components will be there. So this critical threshold is actually independent of this lambda parameter, but it will depend heavily on the underlying dimension. So in the literature, there are already some results about this at least for the Voronoi model, not so much for the Gabriel model. That's not so well studied. So one result is that the critical threshold is non-trivial in the sense that it is strictly in between 0 and 1 if the dimension is larger than 2. Like if the dimension is 1, the critical probability is 1, because then it's very easy to block an infinite component, because just one cell has to be not black, and then it instantly blocks the infinite component. So dimension 1 is not so interesting for us, but for the other dimensions, it's an interesting threshold because it lies in between the two obvious or like the two simple parameters for P. Then what's also known is that if an infinite component exists, so if like P is above this critical threshold, the infinite component is unique. So there are not 2 or 3 or many infinite components. There's just one of them. And so what is also known for dimension 2, there's actually a precise value known. So in dimension 2, it's the value of PC is 1/2. And at criticality, there is no infinite component almost surely. So like above PC, that's it's obvious that there can be infinite components, but like at PC, it's very hard to say something about that. And most of the time, it's very difficult to have precise values for PC. And this is very typical that you can set something for dimension 2 in percolation theory, because there you can use like some dual arguments. And for example, use that if you have a left-right crossing in a box of black points, of black cells, this blocks any top-bottom crossing. And this is used a lot of times in proofs. And then at P exactly 1/2, you kind of have like some sort of symmetry where like the colors and the non-colored cells, they're kind of, or clusters, they're kind of similar to each other. So this is a very classical, and this result would also hold for Bernoulli bond percolation in 2 dimensions. They're exactly same result as well. Then there also have been studied the question for larger dimensions. There exists for if the dimension is large enough, there exists lower and upper bounds on PC. So you can, the precise values here are not so important. You have to remember them, but maybe like the 2 to the minus c leading order term on both sides, they will show up later as well. And this is very classical in percolation, that you can say something in 2 dimensions using dual arguments and for very large dimensions. And we will see later why, you can say something for large dimensions. But maybe any questions or? All right, so our main result was an improvement on this last thing here. So we show for both Poisson-Voronoi percolation and also for the Poisson-Gabriel percolation, how this critical threshold behaves asymptotically as the dimension goes to infinity. So we get here for the Poisson-Voronoi model that it's E divided by B times 2 to the D. And for the Poisson-Gabriel graph, it is 1 divided by 2 to the D. And maybe it already makes some sense that the value for the Poisson-Gabriel graph is a bit larger because this is a subgraph of the other. So the one graph has a bit more connections, and then it is kind of easier to form an infinite component. So then the critical values should be a bit lower. And what would also maybe make sense is that it decreases to 0, because for larger dimensions you have more neighbors, and then it's also easier to form an infinite component. So yeah, those are like our 2 main results. And Okay, now I want to say a bit why you want to study this in large dimensions. So the key fact is that in large dimensions, the clusters, the loops in the clusters, they only play a very small role, and you can kind of ignore them if the dimension is large enough. And then the clusters, they kind of look like trees, which makes proofs very easy in the analysis, because then you have a strong level of independence. Because otherwise, when in low dimensions, to let's say explore a cluster, you come back many times to the point where you already started. This creates some dependence. This very hard, in your proofs to deal with that. But in large dimensions, while loops still always occur, they are so rare that they will not really change the behavior of the model. And the graph where there are no loops is of course a tree. And also, like for a tree, to compute the exact value of PC is quite easy. So here you see a tree where every vertex has degree 4. And in general, if you have a k-regular tree where every vertex has degree k, the critical value, and then you do again side percolation on this graph, on this tree, then the critical value is 1 divided by k minus 1. Because what you can think about is, you can think about the tree hanging at one point, and then every vertex has k minus 1 offsprings. And there's like this famous result that you maybe like saw in some probability course, that you have like some branching process. The threshold for like an infinite component is always when the expected number of offsprings is 1. So then this 1 divided by k minus 1 is exactly the threshold where if you set p to this, the expected number of offsprings is 1. So then this is the threshold after which an infinite component can occur in a tree. And the reason why it's so easy to compute here is exactly because the different connections, they are completely independent from another, because there are no loops in the graph. And you have the same idea on picture also in a lot of high dimensional percolation models. And if you believe me this, then the next result is maybe also not so surprising. So for the usual model that people study, so like the ZD graph that I showed you at the beginning, this has been studied, how the critical probability behaves for large dimensions, and it's here. So like multiple authors showed this around 1990s, like with different proofs, and it's 1 divided by 2 to the d. And this maybe makes sense, because if you look at ZD, every point has 2d neighbors. So then again, if you believe me that it's could look like a tree, then this would be kind of the threshold that you would expect. Because then, the expected number of neighbors is exactly 1 if you set p to be this number. And also the funny thing is, like, because it's a tree, it doesn't matter if you look at bond percolation, so you color the edges, or if you color the sides, it will be the same value. So like this value holds for both of these cases. So the problem is a bit like for our model is that in our model, the graph is random, right? And there's like no, so you cannot really say, okay, what's now the degree? Because the degree is like every point has a different degree. And for our models, the degree is even unbounded. So it's not so easy to maybe like say what you would expect for the Poisson-Voronoi model or for the Gabriel graph. But there's a slightly,
One question. So is it like a law of large numbers thing? So is it the average that we are seeing, the 1 over d or the e over 2d? So it is like the mean degree, or is it something?
Yes. So you already know the next slide.
Oh, sorry.
No, that's a good question. Yeah, but because this is exactly what will show up. That's what you have to. Yeah, you have to. Well, I just show you this next slide, and I think that just answers your question. So what you do is you add a deterministic point, maybe it's like to the origin, but you can put it anywhere else you want, and then this deterministic point is called typical point. And then you look at the Voronoi tessellation of this bigger point process. So you have then the typical point, this is the deterministic point, and also all the other random points. And then you just do the same Voronoi tessellation construction that we had at the beginning. And then the number of neighbors of this typical point is then called the typical degree. And now the expected typical degree has exactly the property that you know that you already predicted. It has the property to act as like some sort of average degree. So what you can do is, if the degree denotes the number of neighbors, so either in the Delaunay graph or Gabriel graph, it works in both cases. And then you sum up all the degrees in some large ball with radius n. And then you normalize with respect to how many points you have in this ball. So this left-hand side here is just the average number, the average degree in a ball of radius n. And if you then let the ball grow to infinity, then this will converge almost surely to a real number, and the real number is the expected typical degree. So the expected number of neighbors of the typical point. And it was quite funny. Actually, you could have also, I chose the property of degree here, but you can also use a different property here. It will then also hold for other cases. So like this point is called typical point, because in the limit, it captures basically all, it captures the average of basically all properties that you can wish for. But here we are in degree. And yeah, this is what you then get. So that's like kind of the average degree. And okay, now maybe you want to the question or
No, it's just a sound thing. You should keep going.
So now we are, of course, maybe interested in the exact value of this for both of our models. And for the Gabriel graph, it's quite easy. And the reason why it's quite easy is because we have this fixed ball. And if you know the Mackey formula, the Mackey formula is written here. It's very, very useful if you want to compute the expectation of things. Like in our case, the function f just counts if there's a connection of x and the typical point. And with the Mackey formula, it's quite easy. And the expected number, the expected typical degree in the Gabriel model is just 2 to the d, and it holds in all dimensions. For the Voronoi model, it's not so easy. And so far, it was only like known in dimension 2, where the value is 6, and in dimension 3, where it's like some very ugly fraction. And what we show is, we show how the expected typical degree behaves as the dimension grows to infinity. So it's b times 2 to the d divided by e. And I hope you all paid attention. We already saw those numbers before. And this is exactly 1 divided by the critical probability for large dimensions. And so, with like those, if you combine those two slides, you just get that the critical probability times the expected typical degree will converge to 1 as d goes to infinity. Exactly what one would expect in a tree if the connections occur independently from another. Right, so now I want to maybe say a bit more things about like what we use in our proofs, and like, or maybe give some intuition what we use in our proofs. Because like one big problem, especially for the Poisson-Voronoi model, is that it has very long range dependencies. Because it doesn't matter how far away 2 points lie in the Euclidean space, there's always a positive probability that they lie in the same Voronoi cell. Of course, it probably will be small if they are very far away, but it's always there. So you have always very long dependencies, which makes a lot of arguments quite hard. But what you can do is, so we can like choose any lambda we want, right? Because PC was independent of it. And what is very nice is if you choose lambda to be 1 divided by the volume of the unit ball, because then a lot of times things cancel out, and the expected number of points in a ball of radius r will be just r to the d, which a lot of times makes things quite easy to work with. So if we choose that, and we choose p to be some constant mu divided by the expected typical degree, then you can show that most black neighbors with a very large probability lie at roughly distance 2 from the typical point. And so one bound of this is quite easy. Namely, if you take any if you like, write like this choreographic ZB for all the black points, and if I fix some radius R that is less than 2, and then I just look at, okay, how many points are in a ball of radius R? How many black points are in this ball? I can just calculate the expectation. It's very easy because it's now a Poisson point process. So you just get that this is P times R to the D, but P was like this, right? And the expected typically always had this leading order term of like 2 to the D. And if R is strictly less than 2, then this will just go to 0. So the reason why we don't have any black points that are closer than 2 to the typical point is just, okay, in expectation there are, you will not find any black points that are closer. And for points that are further away, they always require either a very big Delaunay ball or a very big Gabriel ball that is empty of points. And if they're further away, this will not happen because then the ball has to be too big and you will always find a point inside there for large dimensions. There's like one very important thing that we use all the time, and that's called a measure concentration high dimensions. So you maybe already saw this. So this basically says if you pick a point uniformly at random on the d-dimensional sphere or d-1 dimensional sphere in d dimensions, and then you look at the angle that this uniform point makes with some fixed deterministic point, then most of the time the angle will be roughly 90 degrees. Or in other words, the probability that the angle is not roughly 90 degrees, this will decrease exponentially fast in the dimension. And this has major consequences. We use this a lot of times. And you can use this to show that because you just have polynomial many black points in a ball of radius 2, then you can use this to show that most black points will have an angle of roughly 90 degrees to another. And this is very important because this also has a corollary, namely the following. If you have two balls in d dimensions and you put them at some distance to another, and then you look at the volume of the intersection. Here's like the volume of the intersection of the two balls, and they have to lie at some distance. Then the intersection, the volume of the intersection is exponentially small in the dimension compared to the volume of the whole ball. And this is quite important for us because for any connections that we look at, doesn't matter if it's the Gabriel graph or the Delaunay graph, there always had to be this ball that has to be free of the Poisson points. And if now the intersection, so the intersection is exactly the area where the connections would depend on another. If now the intersection has exponentially small volume in the dimension, this means that for large dimensions, the connections, they kind of behave independently from another. So I was also like summarize this in this picture. So here you have like the typical point and two black neighbors. They are at roughly distance 2 from the typical point. And the black neighbors, they are at roughly 90 degrees to another. And here I've drawn the Gabriel balls to make it a bit easier. And the Gabriel balls will have some intersection here. And this intersection that I colored here, this is the volume of this intersection is exponentially small in the dimension compared to the whole ball, which will mean that the connection will only depend very weakly to another. And this is kind of the reason why a lot of our proofs work if we let the dimension grow, but it would not work for smaller dimensions. Right now, I want to, like, in the final few minutes, I want to kind of go over the strategy of our proof. So we do this kind of in 2 steps. So first, so again, we pick this p as before. So it's some constant mu divided by the expected typical degree. And in the first step, we let this mu to be bigger than 1. And then we show, okay, if mu is slightly bigger than 1, then we can choose a dimension large enough such that with probability 1, there will be an infinite component. And by the definition of the critical parameter, this means, okay, our P was a bit too big to be the critical parameter. So then PC has to be a bit smaller than that. Because already for this P, there can be an infinite component. So yeah, it has to be small. It cannot be larger than P, of course. And then in the second step, we do exactly the opposite thing. We choose mu to be less than 1. And then we show that, okay, if mu is less than 1, then we can increase the dimension sufficiently large, such that almost surely there is no infinite component. And by definition of this critical value, this of course means, okay, it was not good enough. We have to we have to increase P a bit to see infinite components. And if you combine those two things, you get exactly the result that we are after for the.
What's the zero mean? What was that again?
I
forgot.
So here I just mean this is just like
there's non-value.
just,
Okay,
it's
big
just,
enough.
yeah, exactly. Just some large enough value,
Okay.
and it will depend on the specific mu that you take. Okay, so first for the first direction. So using like all those like measure concentration things and like the location of the black neighbors, it's quite easy to show that the number of neighbors will converge in distribution to a Poisson random variable with parameter mu. Because basically what you then do is if the connections are independent, you just throw some independent coin to decide if it's a black neighbor or not. And then the number of neighbors is that follows a Poisson law. So this is the first step that you can do. And then afterwards, you can also iterate this. So you then not only look at the neighbors of the typical point, but then you also want to look at the neighbors of the neighbors and so on. And you can do this up until some fixed generation k. And there you can basically show the same thing, namely that if like the ck are the number of points in the Poisson-Voronoi tessellation or the Delaunay graph of the typical points or all the black points up until some generation k in the graph distance. And then this gk is the independent analog. So the independent analog would be in some branching process in some tree where the connections are completely independent by definition. And then you just say, okay, like how many points are at generation less than k or exactly generation k, doesn't matter. Then this the number of points in our Voronoi or Gabriel model will converge in distribution to the analog where the connections are completely independent from another. But that's so what one might now want to do is, because you might remember this mu was larger than 1, so this is just the offstring distribution of some supercritical branching process, and then you know, okay, the expectation of the random variable is 1. So then you already know basically that, okay, if you do this infinitely long, you will have an infinite component. But the problem here is a bit that this only works for any fixed k. So what you cannot do is you cannot just let k run to infinity and be done. And there are like multiple ways of seeing this. Like one would be to just compare the expected number of points in generation k in the independent model and in our model. So in the independent model, it's very easy. It's just mu to the power of k. Expect number of points at generation k, because in like an average generation you get this mu. And for our case, it is a bit different, because we already know that, okay, most neighbors will lie at distance roughly 2 to the typical point. So then most neighbors of generation k will lie in a ball of roughly 2 times k. But if we then compute the expectation of black points, even of points in this ball, then this will be will be of order k to the power of d. So you see here it's exponential in k, and here it's not exponential in k. So you cannot just let k run to infinity, because it has it grows differently. So at some point it will break, and it only works for every fixed k. So you fix some k, and then you can choose the dimension large enough such that it works sufficiently well, but you cannot kind of do the two limits at the same time here. So then we have to do like something different. So what we do is we define multiple exploration algorithms that explore the neighbors up until distance k and of some fixed point. And the nice thing is that we just have to show that there's an infinite component somewhere. So we can actually ignore all connections that are annoying. So if we can just look at connections that have nice properties. And if the angles are not like we want them to be, or if the points are too close or too far away, or if something else happens that doesn't have like a nice property, we can just ignore it. And what we do is we couple all those exploration algorithms with a side percolation model on Z2. This is kind of just like some helper. So for every single side of this of Z2, we want to run one exploration algorithm that explores the points up until some fixed distance k, and then we restart an exploration again in order to not explore too many points. And every time an exploration has some beneficial result for us, so the angles should be roughly 90 degrees, because this means that locally you kind of move away from the stuff you already explored, because it's always 90 degrees, you will kind of not stick too close to another for too long. And if the exploration algorithms behave nicely, we will open the side in the side percolation model, and we kind of set up the things in a way that if there exists an infinite component in the side percolation model, then also there will be an infinite component in the Voronoi model or in the Gabriel model. And of course, a bit hand wavy here to like not have like too many like technical things on the slides. But yeah, so what also these exploration algorithms should not do is they should not explore too many points. And why this is important is the following, because if there would be too many points, then you can still have a lot of interference of different exploration algorithms that explore different areas. And so, but if those exploration algorithms only explore polynomial in d many points, and one exploration algorithm can also only interfere with exploration algorithms, with polynomial many exploration algorithms around him, then you can use again this measure concentration that we had before, because this measure concentration says that all those intersections where the dependence which is basically the reason for the independence, those intersections, of course, they decay exponentially fast in D. So yeah, if you just have a polynomial many connections that you explore, and only polynomial many other exploration algorithms that you can interfere with, this would then mean that for large dimensions, those exploration algorithms will only have a small interference to another, and then you basically get like a lot of nice trees and nice like branching structures where the connections are nicely behaved, and you can kind of work with that. Right now, I want to come to the other bound. So here we have to do something different. Here we want to use a path counting argument, and we want to show us that the black cluster of this typical point, if we add it to the point process, that this is almost surely finite for those if mu is less than 1, what I had on the previous slide. And then if you have this, you can use this Mackey formula that we had before and translation invariance to show that actually, if this probability is 0, this is already enough to say that almost surely there is no infinite component anywhere in the whole space. So just having one point is actually enough to say this for the whole space. And here it's a bit more difficult, because in this also exploration algorithms, we can basically throw away all the nasty points that have bad properties, because if we can find an infinite structure for the nice points, then of course the infinite structure will also be still there if we also include the bad points. But here we want to say that there's no infinite component. So you really have to use all the points that are there, because yeah, maybe with the bad points, the infinite structure suddenly arises, and this makes it a bit more difficult. And so you want to basically compute the expected number of paths starting from this typical point where all the points of the path is black, and then say that this expected number is kind of decreasing with the dimension. And it's what you also have to take into account, that this path that you are looking at, it could come back a lot of times to places where you were already in the past, and this will again create some dependencies that you never want if you analyze those things. So you have to be kind of think about how you do this. So one way would be that you actually add more edges that are actually there in the path, because if you show this result that there is no infinite component with even more edges, then of course there can also not be an infinite component if you remove the edges again. So you have a picture where so x and y are here, and then you have this Delaunay ball here. And the problem is that this Delaunay ball could be very big. It could be arbitrarily big. And this would be very annoying to work with. But what you can do is you can then look at the Gabriel ball, which is here in red. Then you observe that actually in the Gabriel ball, there's always a half space here that is inside the Delaunay ball. So what you can now say is, okay, in the path, I actually say that a connection is there if in the Gabriel ball there exists a half space that is empty of Poisson points. Because a Delaunay ball that is empty of Poisson points will imply that in the Gabriel ball there has to be a half space that is empty of Poisson points. And the nice thing is now that if you just look at this, you can just look at a bounded area, and you don't have to look at the whole space. This makes a huge difference. And then, of course, you now have added some edges that are not there in the original model, but this doesn't matter, because we just want to say that there's no infinite component, and if you have too many edges, and you can show it for this, that's already good enough. And yeah, this is very helpful, because otherwise you would have to look at the whole space to say if 2 points are connected or not, if you're unlucky. And here you just have to reveal the points inside a bounded area, and it's also a deterministic area, to say if a connection is there or not. And then you define those paths with this with those basically more like general edges that also include some connections that would be technically not there. And then if you have this path, you can kind of define the last point until where you kind of interfere with stuff that it was previously, because maybe it comes back many times, but you can show that this will only occur a finite amount of time. And then you can basically restart at the last point where you interfered with area that you have explored before. And then you split this path into multiple parts, such that those multiple parts can only interfere with parts that are next to it, and not over like very long ranges. And then you want to again compute the expectation of those parts using the more like general edges, where you just have to look at the bounded area. And then we use the multivariate version of the Mackey formula we had before a lot of times, to then show that the expectation of those more general paths is actually decreasing to 0 with the dimension. And then we conclude that, okay, the cluster of the black cluster of the typical point is finite almost surely, and there can be no infinite component. And then, that kind of concludes the lower bound on PC. And then we combine those two things, and then we showed our theorem. Right, that's it. Thanks for listening, and I'm happy to answer any questions.
Certain question. So the first one, in your last proof, I was a little bit confused. So you created this new graph, which is like you make more lines than in the
Yeah.
table graph, no?
Yeah. So here it's basically yeah, like the problem only arises if you look at the Voronoi model, because the Gabriel model you just have to look at this deterministic ball anyway. Yeah, and like in the Voronoi case you just say, okay, I connect X and Y if there's just a half space.
So you created this new graph, and you are essentially claiming that it has the same PC, or almost the same PC. So is
Yeah.
that what you are?
Yeah, I mean, so like this is basically what you do for the long edges, because if X and Y are very far away,
Yes.
then this is kind of the case. But for shorter edges, you kind of have to do
So you're
something
not
else.
okay. I see.
So I don't claim this, no, because for short edge you actually have to do something else, but it was a bit too much for this.
No. But I see. So it's just like long edges, you
Yes.
have to do that.
Yeah.
The other things, do you have sharpness? Like, do you have exponential decay of below PC? Exponential decay of
Yeah, so this is also like this is already known here in the literature that you have so below PC you have this exponentially decaying component. Yeah, exactly, and like and above PC you have this supercritical sharpness, that the probability that you have a finite component but it's larger than n is also quite small.
So and there are these somehow now people know how to compute these like these exponents for high dimensional percolation.
Yeah.
Do you know something about this?
So yeah, I talked to Manuel about that, and he said so because I had this idea for some post applications, but I always got rejected. So I guess it's a bad idea. But I think it would be probably very, very hard. So it's not known. So I know that it's not known, but it's probably very, very difficult. Yeah. But but I'm expecting the critical exponents are exactly the same as for ZD. Pretty sure about that. Yeah.
Thank you. Other question? On Zoom, I cannot check. Let me. I don't know how to check.
No, I don't.
I don't see any.
I don't think so.
If one changes, I guess one can do Voronoi with a different norm instead of L2.
Yeah.
I guess this is not very dependent on that, or it's very interesting.
No, I think
The constant I would believe changes.
yeah, I mean, I think it's interesting, but I'm not
The
sure.
constant.
I mean, you have to check the amount of
the asymptotics.
how many neighbors you have.
Of neighbors.
I think it should change,
Yeah.
but I've never thought about this, but I think it's interesting, yeah.
I mean, I don't know if you're using some. L2 is nice.
Yeah.
It's not. Yeah, I guess maybe it gets hard because
Yeah, like
you
this
use
matter
rotation invariance that you're already using for Poisson somehow.
yeah.
It makes a lot.
I mean, yeah. Also, then like I don't know how like all this measure concentration would look like there. I'm not sure. But like so basically all those like this whole structure is basically everything is just like a corollary from this fact that this uniform point on a sphere is and like a fixed point is roughly 90 degrees. Like everything is just a corollary out of that basically all the time. So I'm not sure how it would like look for other spheres, but probably something similar. I don't know.
Regarding this 90 degrees, it means like really Voronoi becomes closer and closer to CD. Like because Voronoi is 2, it's not that.
Yeah, I mean, but just like for, I mean, like not with the number of neighbors, of course, but Yeah, but maybe just like, yeah, I mean, like you have the 90 degrees, but I think it still looks different from ZT because of the number of neighbors.
Other questions? So if not, let's figure it out.